Hey everyone, in this AP Chem series video, we're going to learn how to interpret a slightly more complex mass spectrum. So remember from the last video, we took a close-up look at boron's mass spectrum. It's got these two peaks here shown in blue, and since each peak corresponds with particles of different mass, I learned that boron atoms come in two different masses, otherwise known as isotopes, boron 10 and boron 11. And since peak height corresponds to abundance, I know that the boron 10 isotope is much more abundant. In particular, it makes up 81.3% of the whole sample, the boron 11, the other 18.7%. In this video, we're going to interpret a second mass spectrum, this time a slightly more complex example. So here we're talking about a sample of chlorine gas, that's Cl2. If you put chlorine gas through a mass spectrometer, it's going to produce something like the mass spectrum shown below. Right away, you'll notice it seems a little bit more complex. I have 5 distinct separate peaks that we have to explain and account for. Now the first thing to notice here with chlorine is that we're not actually testing chlorine atoms because chlorine is a diatomic element, which means it comes in the form of Cl2. So the masses that my mass spectrometer is testing and analyzing aren't the masses of individual chlorine atoms, those are the masses of Cl2 molecules. The next thing we need to know is the type of chlorine isotopes that exist. Luckily for chlorine, it only comes in 2 common isotopic forms, chlorine with a mass of 35 and chlorine with a mass of 37. Now that I know the different isotopes that exist for chlorine, I can start to guess that some of these Cl2 molecules might be made of chlorine atoms where both are the chlorine 35 isotope. That means that the total mass of this Cl2 is 35 plus 35, which is 70, thus explaining the very tall, very abundant peak we see here with a mass of 70. But there's other chlorine isotopes too, so maybe some of the other Cl2 molecules are made of chlorine atoms where both are chlorine 37. This mass will then be 37 plus 37, 74, hence the very small, very uncommon peak we see here at 74. The only other possible makeup for my Cl2 molecules then, we'll label it on this last one, is a chlorine 35 bonded to a chlorine 37. These Cl2s will have a total mass of 72, thus the peak we see here at 72. So that explains these 3 more massive peaks, but we also see 2 smaller peaks down here, somewhere between a mass of 30 and 40. To understand those, you've got to also know that mass spectroscopy is a very violent process. And even though we're primarily testing Cl2 molecules, as they collide with each other and with the inside walls of the spectrometer itself, some of them are going to actually be broken apart into pieces or fragments. So let's say that this Cl2 molecule right here is actually split in 2. That means the mass spectrometer isn't going to read it as a mass of 70 because it no longer exists. The spectrometer will now read the masses of these separated atoms. That explains the peak we see here at 35. This also means that some of my separated chlorine atoms will also be the isotope with a mass of 37, explaining the smaller peak at 37. The idea that molecules can be broken into fragments during mass spectrometry is one of the key ideas for this video. Make sure to pause, write that down. The last thing to notice in this spectrum and some others that you'll see is the vertical axis is not percent abundance, instead it's labeled relative abundance. All that means is that the peak height indicates relative comparisons in amount, not actual percentages. This means that I can't go to the height of this peak, follow it over to the axis, and look up the exact percentage that that particle makes up in the sample. What I can do, however, is see that this chlorine 35 peak is about 3 times as tall as the chlorine 37 peak. This means that relatively there must be 3 times as much chlorine 35 as chlorine 37. That wraps it up for this video. Thanks a lot for watching. Here's a brief summary.